Hello all, I am Priyanka Sundaram and I am going to explain the K-server problem along with my teammate Rishita. I am going to start with the motivation and explain what a competitive analysis is, and just to give an insight about an online algorithm and its competitive analysis, we have taken an example of ski rental problem which I will be explaining, and also I'll give an introduction to the K-server problem and its application. The K-server algorithms and its competitive analysis will be explained by Rishita. In classical optimization, we are given a problem with a specific input and asked to compute the optimal solution for that input. But in real life applications, it is not realistic to have the whole input beforehand. Such kind of problems are called the online problems. Moving on to the competitive analysis, it is a measure to evaluate the performance of online algorithms as compared to its optimal offline solution. If for each request, the cost of online is less than or equal to R times the cost of optimal offline algorithm, then we say that the online algorithm is R competitive. Coming to the ski rental problem, in this problem, you have to make a decision either to buy or rent a ski. The problem here is that the number of days you will ski is not known in advance. Our goal is to minimize the total cost. Assume that buying a ski costs B dollars and renting it costs $1 per day. Our strategy here is that we choose a number k, and until the k minus 1th time you will be renting the skis, and after k minus 1 you will buy them. By doing this, we claim that setting k is equal to b guarantees that we never pay more than twice the cost of the offline strategy. Let's take an example. Assume that b is equal to $7. Thus, according to our strategy, after 6 times, you will buy the skis. So the total cost here is 6 plus 7, which is $13. Let's prove the claim. Consider you are buying the skis in your kth visit, and even if you quit right after this time, the number of times here is greater than or equal to b, and the total payment is k minus 1 plus b, that is 2b minus 1, since we set k is equal to b in our claim. If you knew the number of times you would ski in advance, then you would choose either to buy or rent the ski accordingly. This here is the offline optimal algorithm. The offline cost would be minimum of t comma b, which is b here. And the competitive ratio here is 2b minus 1 over b, where 2b minus 1 is for the online algorithm and b is for the optimal offline algorithm, which is nothing but 2 minus 1 over b, and we conclude that the online strategy is 2 minus 1 over b competitive. Coming to the K-server problem, in this there are k greater than 1 number of servers. M is the metric space with a metric D. Just to recap what a metric space is, it has 4 properties. First is that the distance from a point to itself is 0. Second property is that the distance between two distinct points is positive. Third property is that the distance from a point A to point B is same as the distance from B to A. And finally, the distance in the path going directly from A to B is no more than the distance in any path going from A to B through a third point. Our servers in the K-server problem are located at points of M, which is in the metric space. And a request sequence consists of requests from points of M. The request is served by moving the server to the request, and the cost is determined by the total distance traveled by the servers. Our goal here is to minimize the total cost. Let us take an example graph. Here sigma is our request sequence. The servers are present at B, M, L and J initially. and consider distance between any two nodes as 1. Our first request is at S, so we should move any of the 4 servers to S. Say we are moving the server from B to S. So here the total cost is 2. Next request is at M. Since we already have a server there, the cost of serving M is 0. Next request is at K. We can either move the server from J, L, M or S, which will give the same cost too. Say we are moving the server from J to K. The next request is at A. We can move either K, M or L, which all have cost 1. Similarly, we do for all our requests. This is how all requests are served. Let us look at an application of K-server problem, which is paging. The paging problem is a special case of K-server problem in a uniform metric. The uniform metric is nothing but the distances between distinct points there are 1. Here, the K servers correspond to K slots in the cache and the pages correspond to the nodes. Evicting a page from the cache and bringing a new one maps to moving a server between the corresponding nodes at a cost 1. Next slides will be explained by Rishita.
Hello everyone, I am Rishita. I will be talking about various algorithms to solve K-server problem. In general, there are two broad categories of solving online version of K-server problem. One is deterministic and the other is randomized. In this video, we will be looking at only deterministic way of solving this problem. To start off, we'll discuss greedy approach. This algorithm moves the closest server to the requested location. Let's understand this using an example. Assume the nodes you see in the graph are the possible points in a metric space, meaning that these are the locations where a server can exist. And you have 4 servers at locations M, B, L, and J. Here, sigma indicates the requested sequence. As you can see, the first request that has arrived is S. According to the greedy approach, we will have to move the closest server to S to serve the request. In this example, it is clearly evident that the closest server to S is B. But greedy algorithm will always not give us an optimal solution. To understand this, let's look at another example. Consider there are 3 points in a metric space and we have 2 server locations at points A and B. Our request sequence here is C, BA, 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 and so on. So the first request is C, and all the other are repetitions of pair B and A. If you apply greedy algorithm, then to serve the first request, which is C, you would have to move the closest server, which is the server at location B. To serve the next request, which is B, you would have to move a server at A because it is the closest server to location B. Similarly, to serve the location request A, you will have to move the server at B to A. That means one server will always stay at C and the other server will keep on shifting between A and B. That means as your request sequence will grow, the cost of moving the servers will also grow. To understand the competitive ratio of the greedy algorithm, we will look at optimal offline algorithm, which assumes that it has all input or request sequence beforehand. For the same example, if you would already know that except for the first request, all the others would be AB, then you would place the servers at AB initially. So the cost that will be incurred will be to move the server from B to C and then back to B. That means the cost will remain constant, though your input will increase. According to the definition of competitiveness, the ratio of cost of greedy approach and optimal offline solution is unbounded. But there is one algorithm called work function which has improved performance over greedy with a bounded competitive ratio. The work function is driven by this equation, which is WR of C equal to min of WC minus x plus R plus D of x comma R. In this equation, C is the current configuration. Configuration is nothing but placement of servers in some order in a metric space. Here X implies any server location that belongs to C. In this equation, X is the variant. W of C implies the minimal cost of serving request R and ending up in configuration C when you start from an initial configuration C dash. Sigma I is a request sequence with I number of requests. Here, the term d of x comma r is a distance between two servers located at x and r. This means that we are computing the total distance that would be incurred if we move a server from x in configuration C to r. If you remove w of c minus x plus r from the equation, the remaining part is min of d of x comma r, which is nothing but finding out the closest server x to move to the location r. This is what exactly greedy algorithm does. If you remove w of c minus x plus r from the equation here, you will be left with w of if you remove d of x comma r from the equation, you will have a minimum of w of c minus x plus r left. Here w of c minus x plus r is the minimal cost incurred to reach c minus x plus r from initial configuration. That means we are finding a configuration such that it can be served it can serve the new request R along with the previously seen request in the most optimal way. In a way, it is mimicking the optimal offline algorithm. As you can see, work function algorithm is an aggregation of solutions of both greedy algorithm and optimal offline algorithm. To understand this algorithm, let's look at another example. Suppose the metric space has 5 points and we have 3 servers. So we have in total 5C3 possible combinations of server locations. Assume our servers are initially located at A, B, and C. Our request sequence is E, D, A, B, C for this example. Here, W0 of C indicates work function of configuration C before you get any request. So the first row of this table indicates W0 of all the possible configurations. Since our initial configuration is ABC, W0 of ABC will be 0. To compute W0 of ABD, we just have to compute the distance between configurations ABC and ABD, which clearly from the figure here is 1. Similarly, you'll have to compute W0 of all the other configurations as well. Next, if you look at W1 of C, it indicates work function of configuration C after you have served first request and ended up in configuration C. Let's look at the computation. So W1 of ABC can be computed by by using the formula that we have stated here before. So this is minimum of W0 of EBC plus DAE plus, comma W0 of AEC plus D of B comma E and W0 of ABE plus D of C comma E. So basically we are looking at the costs of getting to ABC if your initial configurations were EBC, AEC, ABE. You can obtain these 3 configurations by removing one node from ABC and replacing it with E. For example, if you remove A from ABC and replace it with E, you'll have EBC. If you replace B with E, you'll have AEC. If you replace C with E, you'll have ABE. Since values of all the configurations here are 4. So you can remove any node from this configuration and replace it with E. Let's try and interpret this table here. To understand this, let's look at an example. The value of W1 of A, B, C here is 4 of A. That means 4 is the cost that is taken to reach ABC after serving request E. And the previous configuration that will give you the best way to reach ABC will be can be obtained by replacing A with E, which is BCE. And similarly, if you look at W2 of ABC, the best possible way to reach ABC after serving request 2 would be BCD, that is replacing A with the second request, that is D. So the overall path would be ABC to BCE to ABC for W1 of ABC, and from ABC to BCD to ABC for W2 of ABC. Now, lastly, work function algorithm has a computative ratio of 2k minus 1 for any value of k and for any metric space. There is a conjecture for the k-server problem, which is for more specifically for deterministic k-server problem, which states that for any metric space, there is a deterministic algorithm with computative ratio of k. That means the best algorithm to solve k-server problem deterministically is having a computative ratio of k. There has been no detailed proof yet, but as of now, work function algorithm is the best known algorithm to solve k-server problem deterministically. These are few references which we found useful while we were researching about k-server problem. Thank you.